Okay, students. So this is a video that is meant to be a resource for you as you're working through the worksheet that you're doing in class today. The worksheet is set up in the same sequence as the topics are covered on the video. So you might want to watch a little bit of the video, take some notes on the content, go to the worksheet, answer some questions. Come back to the video, take some notes on the content, go to the worksheet, answer some questions. Or you could have the worksheet open if you have the capacity to do that while you're watching the video and see where the answers to the worksheet questions are coming up in the video. So I hope this helps. Sorry that I'm not able to be in class. I'm getting a broken tooth fixed, or at least evaluated. All right? So don't forget, bird sounds and high fives. Good for your spirit and your emotions. So high fives and bird sounds. Okay, the first part of this video is going to help us review how you use the periodic table to figure out electron configurations. We understand that the electron configurations, the way the electrons are arranged around the nucleus for an atom, is one of the most important things that determines how the atoms behave. And what is our quest? Our quest is to understand in the best way that we can on a basic level atomic behavior. So that's why we're looking at this, and this is going to be review. We've touched on this a little bit already, but we're going to go into it in much more depth and give you the opportunity to practice it more. Okay? So hang in there. Sorry for the video, but hopefully this is helpful in completing the worksheet that you're working on in class today. So here's our periodic table. It's got all of our elements, all 118 of them, and each one of these 118 elements has its own unique arrangement of electrons. So we like to be able to express how those electrons are arranged. We know we have that chart, figure 5.11 in the textbook, that shows us the order, the sequence in which electrons are going to occupy different main energy levels and sublevels from low energy to high energy levels. The periodic table also is a tool that allows us to do this, and this is how it works. If we take the simplest element with the simplest atom, we would look at hydrogen with one proton in the nucleus, one electron in the first main energy level, S sublevel. So this first period on the periodic table represents the first main energy level, and the first sublevel is an S. So we put one electron in there for hydrogen. When we move over to helium, which is all the way over here, we're still on the first period, that first row on the periodic table, but we're now 2 electrons in the first main energy level, S sublevel. That completes the first main energy level because it only has an S sublevel. Notice that we're at the end of the periodic table over here at the noble gases. Helium is a noble gas. It has 2 valence electrons. Those are in the first main energy level, S sublevel, and there's no more room for electrons in that main energy level. So as we go through the periodic table, our next stop is lithium. But now we're in the second period of the periodic table, so we've started the second main energy level, where we start with an S. So we put 1 in the S, 2 in the S for beryllium. Then we jump over the gap here. After the second main energy level, S sublevel, is filled, we have to go to the second main energy level, P sublevel. So as we go across this row from boron to neon, we are putting electrons into the second main energy level, P sublevel, and we can put 1, 2, 3, 4, 5, 6 electrons there. Notice that we are now at neon, which is the next noble gas. We've completed the second main energy level by putting 2 in the S, 6 in the P. The next place we go is to the third main energy level, and we start with an S sublevel. We put 1 in the 3S, 2 in the 3s. Then we jump over here and we start going into the 3p. We go all the way across with 6. We get to argon, the next noble gas. We've completed the third main energy level at that point, and we go down to the next period and start the fourth main energy level with an S. So really important to note, we always finish an outermost main energy level with the P's and start a new outermost main energy level with an S. We put 2 electrons in the S before we move on. At this point, notice that we don't get to go to the 4 P's. The 4 P's would be here, the 5 P's would be here, the 6 P's would be here, and the 7 P's. So these are 4P, 5P, 6P, 7P. But we don't get to the 4 P's until we go through this row of elements, and these are the 3D elements. These would be the 4D elements. Here we would have the 5D, the 6D, and so on. So we've got 1s, 2s, 3s, 4s, down to 7s. So this is our S block. When we're dealing with the alkali metals and the alkaline earth metals, we're putting the highest energy electrons into the outermost main energy level, S sublevel. 1s, 2s, 3s, 4s, 5s, 6s, 7s. We go from the 1s to the 2s, to the 2p, to the 3s, to the 3p, all the way over to argon, to the 4s, then we go to the 3d, 10 electrons, then we go into the 4p, finish with the noble gas, then we start a new outermost main energy level, 5s, then we go through the 4ds, into the 5ps, we end at the noble gases. So here are the noble gases. Notice that we are always completing an outermost main energy level when we get to the noble gases. The outermost main energy level is filled. That's that noble gas configuration that we have already discussed is the lowest possible energy state. That's what the atoms want. They want that noble gas configuration. Because then they have a filled outermost main energy level. There's no more space for additional electrons, and it's a very stable state. So that leaves the last question, what's down here? So these are the F's. So we have 4F and 5F as we go across here. I don't want to spend too much time on the F's right now, but you should be aware that these are down here. If you were following the yellow brick road, as we say, when you come off of barium, you go down here to 57 to lanthanum and all the way through the 4Fs. So what that means is after the 6S, before you get to the 5Ds, you're going through the 4Fs and then coming back from lutetium here, 71, to hafnium here, 72. Then you go 5Ds, then you get to the 6Ps. Obviously, as you add more electrons going down the periodic table, things get more complex. So that's how we use the periodic table to figure out what the electron configuration is. If we take a specific example, arsenic. Arsenic is right here. So I know the last 3 electrons are going into the 4th main energy level, P sublevel. So I'm going to end the configuration with 4p3. To get there, I've got to go 1s2, 2s2, 2p, 6. 3s has 2. 3p has 6. 4s has 2. 3d has 10. 4p has 1, 2, 3. Another example we could use would be carbon. Carbon's going to end in the second p, second main energy level, p sublevel. It's going to have 2 electrons there. I got to go through the 1s, where I got 1 for the hydrogen, 2 for the helium. That's 2 electrons. I got to go through the 2s with 2 electrons, and then I put 2 electrons in the 2p. So what does that look like if we do the box diagram? I've got the 1s, I've got the 2s, I've got the 2p. And I've got 2 electrons in the 1s, hydrogen and helium. I've got 2 electrons in the 2s, gets me through lithium and beryllium. Then I get over here to the second main energy level p, 1, 2 electrons, 1 in each orbital before you double them up. That's a lower energy state than doubling them up in the same. Okay? So, take a look at the worksheet, use the periodic table, and practice doing the electron configurations that are indicated on the worksheet. So that leads us to the question, where to next? What do we do with our understanding and our learning about atomic behaviors? We talk about periodic trends. Those are trends in properties that recur. So there's a period. We see an increase or a decrease or whatever the change and the trend may be, and it's repeating. So small to big, back to small to big, back to small to big. So there's a recurrence, a periodic change or growth or fluctuation in some sort of a property, size and different properties and things like that. So we'll talk about those one at a time. Number of valence electrons. The number of valence electrons is a periodic trend. We start with the alkali metals on the left-hand side of the periodic table, and we have 1 valence electron in the S sublevel. And then we have 2 valence electrons for the alkaline earth metals, and so on as we progress across the periodic table. Let's take a look at the periodic table. So here, hydrogen has 1 valence electron, lithium has 1 valence electron, all of these alkali metals have 1 valence electron. Then we put a second valence electron in the S sublevel for helium, way over there, or beryllium, magnesium, calcium, strontium, barium, and radium. These are the alkaline earth metals. They have 2 valence electrons. Then let's jump all the way over to boron. Boron has 2 in the S, 1 in the P, so it has 3 valence electrons. Carbon has 2 in the S, 2 in the P for 4 valence electrons. Nitrogen has 2 in the S, 3 in the P for 5, and so on. 6, 7, 8. And we can come back here, we can go sodium, alkali metal, has 1 valence electron, 2 valence electrons, 3 for aluminum, 4 for silicon, 5, 6, 7, 8. Done. Maximum number of electrons you can have in the outermost is 8. 8 valence electrons when it's the outermost main energy level. Noble gas configuration. Then we go to potassium, 2 in the 4s. These are in the third main energy level, which is inner, not the outermost. So all of these electrons are being added to the inner part of the atom rather than the outermost main energy level. So we've got 2 valence electrons, 1 for potassium, 2 for calcium, and all the alkaline earth metals. We get to gallium, 3. So boron, aluminum, and gallium all have 3. All of these going down here, 3 valence electrons, 4 valence electrons, 5, 6, 7, 8. Noble gas configuration, 8 valence electrons. Exception? Helium. It's only got 2 electrons. How can it have 8 valence electrons? But its outermost main energy level is filled. It's the first main energy level. We already talked about effective nuclear charge. and how to find it. But the pro tip is, if you know how many valence electrons, that essentially gives you an idea of what the effective nuclear charge is. So elements that have one valence electron will have an effective nuclear charge of approximately 1. Elements with 4 valence electrons will have an effective nuclear charge of approximately 4. So as we move across the periodic table, the alkali metals and hydrogen, which is not a metal, the alkali metals and hydrogen have 1 valence electron, so they all have an effective nuclear charge of approximately 1, approximately 2. All of these more or less have 2 valence electrons. So they have an effective nuclear charge of roughly 2. 3 valence electrons, effective nuclear charge is roughly 3. 4, 5, 6, you can see it's increasing as we go across. The effective nuclear charge for the halogens, fluorine, chlorine, bromine, iodine, astatine down here. 7. The effective nuclear charge for neon and the other noble gases, 8. So the noble gases have the highest effective nuclear charge acting on their valence electrons. Helium is an exception, it's only got 2 valence electrons, so it has an effective nuclear charge of 2. But it's a very small atom. Okay, so effective nuclear charge is a periodic trend that increases as we go across the periodic table, maxes out here, hits the maximum, and then it drops as we go back over here. So potassium has a lower effective nuclear charge than gallium. Gallium's is lower than bromine. Krypton has the highest along that row. So that's effective nuclear charge, which is really important because, and make note of this, the effective nuclear charge is determining the force of attraction that's being applied to the valence electrons. A lower effective nuclear charge means a weaker attraction for the valence electrons than if you have a higher effective nuclear charge. Check? Good? Go to the worksheet and answer some questions about periodic trends of valence electrons and effective nuclear charge. So just as I mentioned, as the effective nuclear charge increases, the pull on the valence electrons increases. So when we talk about the attraction or the pull on valence electrons, that strength of pull on the valence electrons, it's increasing as we move across the periodic table. Alkali metals have the lowest effective nuclear charge, therefore we consider that they have a weaker attraction or pull on the valence electrons. It only has 1, right? But that 1 valence electron feels a weak pull compared to the noble gases having 8 valence electrons that are strongly pulled on because of that increasing effective nuclear charge moving across the periodic table. The next property that is related, you would think, atomic size. So the electrons are occupying space around the nucleus, right? They're not fixed in any one position. They can expand away and be pulled in closer, and they're constantly moving at very high speeds. The size of the atom is roughly from the center of the atom at the nucleus to whatever the outer portion of that atom is. So think of it this way. The more strongly the valence electrons are pulled on, they're going to be pulled closer to the nucleus. So as the effective nuclear charge increases going left to right across the periodic table, the atoms are going to get smaller. So when we go from left on the periodic table to right on the periodic table, the atomic size is going to get smaller. So if we look at the periodic table, the alkali metals, alkaline earth metals, we would expect to be bigger atoms than as we go across to the noble gases. The other thing that affects the size would be the number of electrons. So there are 2 factors. What is the effective nuclear charge pulling in those electrons, and how many electrons are layered in? Obviously, hydrogen with one valence electron in the first main energy level is going to be smaller than lithium, which has 3 electrons, one in the first, two in the first, and one in the second main energy level. So lithium has a second main energy level, which makes lithium larger than hydrogen. So as we go down, you're adding layers, you're adding main energy levels. So the atoms are going to get larger. So as we go from left to right on the periodic table, we see the atoms being pulled into smaller sizes. When we go from top down, we're adding layers, so they're getting bigger. So from the top down, the atoms get bigger. From the left to the right, the atoms are getting smaller. So that's a periodic trend that you want to pay attention to and understand. So just as I mentioned, as the effective nuclear charge increases, the pull on the valence electrons increases. So when we talk about the attraction or the pull on valence electrons, that strength of pull on the valence electrons, it's increasing as we move across the periodic table. Alkali metals have the lowest effective nuclear charge, therefore we consider that they have a weaker attraction or pull on the valence electrons. It only has one, right? But that one valence electron feels a weak pull compared to the noble gases having 8 valence electrons that are strongly pulled on because of that increasing effective nuclear charge moving across the periodic table. The next property that is related, you would think, atomic size. So the electrons are occupying space around the nucleus, right? They're not fixed in any one position. They can expand away and be pulled in closer, and they're constantly moving at very high speeds. The size of the atom is roughly from the center of the atom at the nucleus to whatever the outer portion of that atom is. So think of it this way. The more strongly the valence electrons are pulled on, they're going to be pulled closer to the nucleus. So as the effective nuclear charge increases going left to right across the periodic table, the atoms are going to get smaller. So when we go from left on the periodic table to right on the periodic table, the atomic size is going to get smaller. So if we look at the periodic table, the alkali metals, alkaline earth metals, we would expect to be bigger atoms than as we go across to the noble gases. The other thing that affects the size would be the number of electrons. So there are 2 factors. What is the effective nuclear charge pulling in those electrons, and how many electrons are layered in? Obviously, hydrogen with 1 valence electron in the first main energy level is going to be smaller than lithium, which has 3 electrons, one in the first, two in the first, and one in the second main energy level. So lithium has a second main energy level, which makes lithium larger than hydrogen. So as we go down, you're adding layers, you're adding main energy levels. So the atoms are going to get larger. So as we go from left to right on the periodic table, we see the atoms being pulled into smaller sizes. When we go from top down, we're adding layers, so they're getting bigger. So from the top down, the atoms get bigger. From the left to the right, the atoms are getting smaller. So that's a periodic trend that you want to pay attention to and understand. Okay, we have 3 more properties to talk about. So remember the idea of elementary school students, middle school students, upper school students, and the variance in behaviors that you would see as you go from 2nd grade to 7th grade to 11th grade, right? We would expect different behaviors. And we're thinking of that metaphorically as representing our idea of atoms and atoms having a variety of different behaviors. So these are atomic behaviors, characteristics, or properties, correct? Got it. So ionization energy, basically what we're looking at here is how difficult is it to remove an electron from an atom. I talked about picking apples. How hard is it to get the apple off of the tree? Ionization energy is describing how difficult it is to remove an electron from an atom. All atoms pull on their electrons. All atoms pull on their electrons. So the question is, how much energy does it take to remove an electron from different atoms? Obviously, that's going to have to do with how strongly they're attracted to the nucleus. It's also going to have to do with their size, which also affects the strength of pull on the electrons. Electrons that are farther from the nucleus but have similar effective nuclear charges are going to be more weakly or less strongly held onto. So easier apples to pick off the tree. So we would expect alkali metals, which have a weak effective nuclear charge, to have lower ionization energies. It's easier to pluck away an electron from an alkali metal. As you go across to the noble gases, it becomes more difficult. So let's look at the periodic table. All right, so over here we have low effective nuclear charges, weaker pull for the 1 valence electron or the 2 valence electrons. And as we go across, we're increasing the strength of pull on those electrons. So it gets harder to remove the electron, harder to pluck that apple off the tree. So easier to pull the electrons off, very difficult to remove the electrons from the noble gases. The halogens, difficult to remove electrons. The oxygen family, difficult to remove the electrons. But it's an increasing amount of strength required to remove electrons as you go across the periodic table. Ionization energy increases. The energy it takes to remove an electron gets higher. If the atom is bigger, as you go down a group, for example, they're farther away from the nucleus, therefore they're actually easier to remove. They're more weakly held onto by the nucleus. So thallium, it's going to be easier to remove the thallium an electron from thallium than it is to remove an electron from boron, which is smaller. So I know this is a lot of information, but it's on video, so you can stop it, you can take a break, you can take a breath, leave it alone for a little bit, and come back to it. So a lot of information, but hopefully it's a good resource. Okay, the next atomic property here is electron affinity. Affinity is a word that means desire for. So this is basically describing an atom's interest or desire for an additional electron. So now you're coming along, you've got this electron that you picked up from some atom somewhere, and you're going up to another atom and you're measuring its interest in gaining an additional electron. Right? So it's a little bit more complex, but obviously this additional electron that you want to add to an atom, there's a couple things that are going to happen. How strongly is it pulled on by that atom's nucleus? And is there room for that additional electron to be added to that atom? What I mean by that last part is there room? So if we look at the periodic table, the noble gases have a completely filled outermost main energy level. There's no more space in that main energy level for an additional electron. So you're not going to be able to add that electron very easily to a noble gas. It's not going to feel much of a strength of attraction. It's going to be very repelled by all the electrons that are there, and it's going to not feel a pull from the nucleus of that atom. And therefore, there's not going to be a way to really get it to add on to that atom. So not a very favorable affinity or desire for an additional electron, basically like a negative affinity, like it's pushing it away. Over here, these elements have weak attraction for their own valence electrons. They do have space for an additional electron, but the attraction is relatively weak because of the low effective nuclear charge. So you can probably add one, but it's not going to be a very vigorous acceptance, not a very high or favorable affinity. But as we go across, we have room to add and an increasing effective nuclear charge. So we have a stronger and stronger affinity for an additional electron. As we get to the halogens, it maxes out. And then we go to the noble gases and they're like, no thank you, no thank you, don't want that additional electron. But the halogens have one space, because they have 5 in the P, they got one more space in that P sublevel, and they have a very high effective nuclear charge, so they can pull that one electron in, and there's room for it. So they're like, yes, please. All right? So the trend is, we don't really want it, but we'll kind of take it, right? We have space, we can pull on it a little bit, but we don't really want it that much. Yes, we're getting more interested in that additional electron. Right up to the halogens, we're like, yeah, you bet we'll take that one electron, because when we get that one electron, we now have a noble gas configuration, which is like, woohoo, what we're striving for, the noble gas configuration. So that's electron affinity. How much does an atom want to gain an additional electron? Different than ionization energy, which is describing how strongly is it holding on to its valence electrons and how much energy do I need to exert to remove it. Make sense? Wow, this is so much information. I am so sorry. But again, video, take your time, pause it, go to the worksheet, come back to the video, go over to the worksheet. If you have questions, go back to the video. And again, we'll have time in class to go over all of this if you're feeling confused. So the last property that we'll discuss is metallic character. So when things act like a metal, we consider them to have a high metallic character. That's like if you're acting like an upper schooler, you have a high representation of upper school student character. If you're acting like an elementary school student, then you're more like an elementary school student or a middle school student than you are an upper school student. Does that make sense? Maybe not, but it's a try, right? So metallic characters, we have to think about what is the character of metals. So there's a long list of things. Metals conduct electricity. Metals are malleable. You can whack them with a hammer and they'll bend and shape and form. Metals have low specific heats. That means they heat up quickly. They cool down quickly. Metals, relevant to what we've been talking about, have a weak attraction for their valence electrons, so it's easy to give them up. And by giving up electrons, they actually dump their valence electrons and end up with a noble gas configuration. Don't worry if you don't grasp that right now. We'll go over it another time. But metals tend to lose electrons. So when we look at metallic character, let's toggle to the periodic table. Where are the most metallic elements? They're going to be the ones that most readily give up valence electrons. So on the left-hand side of the periodic table, these are the most metallic, the alkali metals. Remember that hydrogen is not a metal. It's only over here because it has one valence electron. And chemically, it reacts in similar ways to the alkali metals. But it is a gas. It's not metallic in any way other than the fact that it could lose its one valence electron. So these metals here are the most metallic of all the elements. Then you get the alkaline earth metals. So here we have the most metallic. As we transition, ding, 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 transition metals. Through the transition metals, we have metals and metallic behaviors, and these things like to lose electrons. And as we get to this point, we're transitioning into not very metallic properties, not much metallic character. So we've got the nonmetals over here, including the noble gases. So when we talk about metallic character, high over here, moving to less metallic and not metallic. So high metallic character, not metallic character. High on the left, not metallic on the right. Sound good? So we have metals and we have non-metals, and as we've discussed before, we have semi-metals, things that are sort of metallic, sort of not metallic. So we think of them as semi-metals. So that's our metallic character. Those are the properties that we're working with right now. And the worksheet gives you the opportunity to kind of think on what you've learned and to refer to the video and to answer some questions that we can go over when we have class next. Sound good? All right. Have a good rest of your day. Oh, don't forget, high five, bird sounds. High five and bird sounds.